So we find extrema on a closed interval. Very important that you know this is a closed interval. So we're talking about a function, a continuous function on a closed interval. I don't care what that function looks like, right? But there is a closed interval a and b. At some point in that closed interval, because of the extreme value theorem, you have to reach your highest point and you have to reach your lowest point. So where can those extrema occur? It can happen at the endpoints or it can happen at any of the critical values. So let's see what this says right here. Guidelines for finding extrema on closed intervals. To find an extrema on a continuous function on a closed interval, it has to be continuous and it has to be a closed interval for this to work. What are you going to do? The first thing you're going to do is find the critical numbers. How do you do that? You find f prime of x equal to 0 or undefined. Okay? Then you're going to evaluate each critical number in the interval AB, and then you're going to evaluate the endpoints. So step 1 is find those critical numbers. Step 2 is you're going to plug the CVs and endpoints into the original function f of x. And it's really important that you don't plug them into the derivative, you're plugging them into the original function. And then the last step, which I call step 3, they call step 4, it says the least of these values is the minimum, the greatest is the maximum. So the least is the minimum, the greatest is the maximum. So we can look at this all day long, we can read it all day long. It's so much better if we just put it into practice. It says, example 2, find the extrema of the function f of x equals 3x to the fourth minus 4x cubed on the interval -1 to 2. So let's go ahead and give this a try. The first step that we want to do is we want to find the CVs, the critical values. What are the critical values? Again, those are where the derivative is equal to 0 or undefined. So let's go ahead and find the derivative. F prime of x shouldn't be too hard. Derivative of 3x to the fourth would be 3 times 4, which would be 12x cubed. Minus 4x cubed, the derivative of that is 4 times 3, which would be minus 12x squared. Well, we've set this equal to 0. I'm just going to note to myself, this is a polynomial function, so it's never undefined. That doesn't matter to us right now, but when we start dealing with fractions, it will. So I'm just going to note to myself, I set it equal to 0. It's never undefined. Looks like I can factor out a 12x squared on there. So if I factor out a 12x squared, 12x cubed divided by 12x squared would just be an x, and 12x squared divided by 12x squared would be a 1. So we set that equal to 0. Now we set each one of those terms equal to 0. 12x squared equal to 0. Divide both sides by 12, I'd have x squared equals 0. Take the square root, I'd end up with x equals 0. The other one, I have x minus 1 equals 0. Add 1 to both sides and I get x equals 1. So these right here are my CVs, my critical values, what they call critical numbers. So now I want to consider that interval. What's that interval? The interval is -1 to 2. And I want to make sure my critical values are in that interval. And in this case, they are. Here's a 0 and here's a 1. I only test points in that interval. So what are we going to do now? We're going to move on to step 2. Step 2, I'm going to use the table feature in my calculator. What I do is I take the x values and I plug it into the original function. It's huge that you know it's the original function. So what's the original function? The original function is 3x to the fourth minus 4x cubed. What numbers do I plug in? I plug in every single one of the endpoints and the critical values within the endpoints. So I'm plugging in all 4 of those numbers. Let's plug in -1, 0, 1, and 2. Again, how do I plug those in? I'm going to, on my TI 30XS multi-view calculator, the class calculator, I hit the table button, I clear it out, I'm going to type in 3x to the fourth power, and then I hit the right arrow to get out of the power. I type in minus 4x to the cubed. I hit enter. Start doesn't matter. Step doesn't matter. Make sure you're on ask x and hit OK. And now I'm going to type in the numbers. -1, enter. When I do that, I got a number of 7. 0, enter. When I did that, I got a number of 0. 1, enter. When I did that, I got a value of -1. And then I plug in 2, enter, and I get a value of 16. So now that I have these, I can find my maximums and minimums. Notice that this point here is the highest. That's my highest y value. So that implies 216 is a maximum. So the maximum point occurs at the point on the graph, 216. Let's keep on going. What's the lowest value? Notice of 7, 0, -1, and 16. The lowest value seems to be at the point -1 would be the lowest value. So this is the lowest. So that tells me that the point 1, -1 is a min. So the minimum's at the point 1, -1. Okay? So let's take a step back and make sure you understood everything that just happened. What just happened is we found the critical, well, first of all, we had a continuous function, it's a polynomial function, on a closed interval. Since it's a continuous function on a closed interval, I know it has a max or a min by the extreme value theorem. I find the critical values, which is setting the derivative equal to 0 and undefined. I look at the interval with the endpoints and the critical values within that interval, and I test every point into the original function. The highest of the y values is the maximum. The lowest of the y values is the minimum. So hopefully now that you've actually seen it, this process makes a little more sense, and we can do the next problem a little faster. So let's look at the next one. Problem 3, it says find the extrema of f of x equals 2x minus 3x to the 2/3 on the closed interval -1, 3. Again, this isn't a polynomial function, but I do want to note that this is defined everywhere. It is a cube root, which works for negatives and positives. So this is defined everywhere on the interval from -1 to 3. So it is continuous on a closed interval. Because it's continuous on a closed interval, we know the extreme value theorem says we must have a max or a min. So step 1, again, we want to find those critical values. What are critical values? Critical values are where the derivative is equal to 0 or undefined. So let's find that derivative. The derivative of 2x is 2 times 1, which is just 2. And the derivative of 3 times x to the 2/3 would be 3 times 2/3 x to the -1/3 when I subtract 1. I'm going to clean that up. So my derivative is equal to 2 minus, well, the 3's cancel out. Simplify, I guess I should say. So I have a 2 on top, and then it looks like I have a cube root of x on bottom. Cube root of x on bottom, and that was a subtraction between those two right there. Okay. I need to set this thing equal to 0 or undefined. Well, first of all, where would it be undefined? It would be undefined if the denominator is equal to 0. So let's go ahead and make this a common denominator. So what I'm going to do is I'm going to multiply the top and bottom times the cube root of x for that first term. So when I do that, I would have 2 times the cube root of x minus 2 all over the cube root of x. Again, all I did was get a common denominator, and I'm going to set that equal to 0 or undefined. That's my derivative right there. Okay? So let's think about this. When is this function equal to 0? A fraction is equal to 0 when its numerator equals 0. So that'd be 2 times the cube root of x minus 2 equals 0. So how do we solve that? Add 2 to both sides. I would have 2 times the cube root of x equals 2. Divide both sides by 2. I would have the cube root of x equals, well, 2 divided by 2 would be 1. To get rid of the cube root, you cube both sides. So I'd cube both sides, and I'd end up with x equals 1. So this would be a critical value right here. The next thing I need to do is care about where's the derivative undefined. Well, a derivative is undefined when, or a fraction's undefined when the denominator equals 0. So in this case, when the cube root of x equals 0. So if the cube root of x equals 0, to solve it, I cube both sides, and I end up with x equals 0. Notice x equals 0 is also in my domain of my function, I can plug 0 into the original function because it's in the original function. They're both 1 and 0 can be plugged in. I know that this function's continuous. I know those derivatives exist. I know these are the derivatives don't exist. I know these are critical values where the derivative equals 0 or the derivative exists. Okay? So let's think about that interval. Here's the interval from -1 to 3, and let's consider our critical values. We just got critical values of 0 and 1. So we know the maximum must exist, and it must be at one of those 4 points. We also know the minimum must exist, and it must be at one of those 4 points. So how do we find out? We'll plug those 4 points in to the original function. The original function was 2x minus 3x to the 2/3. What numbers am I plugging in? I'm plugging in those 4 numbers, the endpoints and the critical values between them. That's -1, 0, 1, and 3. I want to plug each one of those numbers in. So I'm going to use the table feature on my calculator. I hit table. I clear out anything I have. I type in 2x minus 3x raised to the, I'm going to do a fraction and do 2/3. I hit enter. Start doesn't matter, step doesn't matter. Make sure you've selected ask x and hit OK. I'm going to type in the first one, -1, enter, and I'm getting a value of -5. 0, enter, I'm getting a value of 0. 1, enter, I'm getting a value of -1. And 3, enter, I'm getting a value of -0.24 and change. Goes on, okay? So what's that mean? Well, what that means to me is we can now find our maximum and our minimum. Think about these 4 y values right here. What is the lowest of those 4 y values? Well, the lowest is -5. So this right here must be my minimum. My minimum must occur at the point -1, -5. Okay? Likewise, I need to look for my highest point. My highest y value, believe it or not, is 0. 0 is the highest y value, so that is my maximum. The point 0, 0 would be my maximum in this case. Okay? So, if you want to see this visually, I highly encourage you to look at the e-text. I highly encourage you to graph this on Desmos, and you could see these graphs on these closed intervals. You could see that we have indeed found these maximums and minimums without even having to look at the graph. That's something very, very powerful, because if we had these in a previous class, like if we had this in college algebra or intermediate algebra, the only way we could find the highest point would be if it was a quadratic, we could find the vertex. But anything else, we had to use our graphing calculator. So we had to use a graphing utility or some type of technology to find maximums and minimums. We were able to find maximums and minimums of a non-polynomial function in example 3, and a polynomial function in example 2. We were able to find maximums and minimums in a matter of a minute or two without ever even looking at the graph. No graphing utilities needed. So very, very cool, very important math that we're doing here.